All right, so I want to recall the unit tangent vector t, and that needs a hat on it, is r prime over length of r prime. And I want to point out for you that this thing is only defined for when r prime of t is not the zero vector. When it's the zero vector, then r prime makes sense, but the unit tangent vector doesn't make sense because you can't divide by zero. So that leads us to a definition. We're going to call the space curve r of t smooth if r prime is continuous and r prime of t is not the zero vector for all points on the curve. Let's say it like that, for all points on the curve. And so what I want to highlight to you is this r prime not being the zero vector really means that there are no cusps on the curve. And you remember talking about cusps back in Calc 1. There's no sharp points like that. All right, so we're going to set that aside for a minute. And so we're going to be talking about smooth curves, and our goal is to try and quantify how curvy a space curve is. There's a difference between this curve that I've drawn and this curve that I've drawn. One of them would make sort of a more boring roller coaster, and one of them would make a more exciting roller coaster. So in some sense, I guess you could say we want to measure the puke factor of a roller coaster. How sick would it make you if you rode it? You know, and the curvier, the worse. All right, and so the key observation here is that if you have a smooth curve C, then the rate of change of the unit tangent vector is directly connected to the curviness of C. So the rate of change, how fast this unit tangent vector is changing is, oops, those aren't tangent, but how fast this unit tangent vector is changing is somehow directly connected to the curviness of C. And I want to point out the length isn't changing, just the direction. So it's sort of swinging like this. That's connected very much to how fast, if you will, C is curving. And so that leads us to a definition. We're going to define the curvature of a space curve C parameterized by r of t as k of t equals, and I'm going to write something down that's going to seem a little strange, but we're going to unpack this and get to some concrete things we can use. So we're going to think of it as the rate of change of the unit tangent vector with respect to arc length. Okay, so let's say that in words. This is the rate of change of the unit tangent vector with respect to arc length. And I'm saying take the length of this thing. And so that's going to produce a scalar. And so the point is the curvature gives you a number. It gives you a scalar, which is measuring how curvy something is at a certain point. And so right away, we want to try and come up with a better formula. It's unclear how we're going to use this in practice. And so I'm going to lead you right now to a formula that we'll use in practice. And so the point is, we saw just in the last video that you can reparameterize r of t with respect to arc length. So we're going to do that. And so we're going to go ahead and think now of r of s, and we're going to think of r of s as the unit tangent vector t, and then we're going to plug in s into that. So I'm just going to take the parameterization for r of s, I'm going to plug that into my unit tangent vector, and I can think about t of s. And now what I want you to realize is this: if I take dt d little t, take the derivative of the unit tangent vector with respect to t, using the chain rule, s is a function of t. And so using the chain rule, I get dt ds dot ds dt by the chain rule. This is classic chain rule. And so the point is, I can solve for this dt ds. That popped out right there. And so the point is dt ds is exactly well, we can think about this as just t prime over s prime. And so this is exactly t prime of t over s prime of t. But now, remember, when we talked about arc length, the arc length function, we said s prime is just the length of r prime. And so this becomes t prime of t over the length of r prime of t. And so that's dt ds. We're interested, of course, in the curvature. and the curvature is going to be the absolute value of that. So the curvature, the key takeaway here, let's put this here. The curvature is going to be the absolute value of, I'm sorry, not absolute value, the length of the derivative of the unit tangent vector t over the length of r prime of t, like this. Actually, we can drop the length on the middle, and we can just do that. So that's what's happening here. And we're going to use this formula and give it a try in the next examples.